All right. So what we're going to be looking at today is Boyles's, Charles's, and the combined gas laws. We actually have already looked at Boyle's and Charles's law, and you guys came up with some equations using our PhET simulation. And so we're going to go ahead and review those ideas and see some examples, and then we're going to be putting them together in what's called the combined gas law problem. What we have seen using our PhET simulation is that there are four variables that we can change. We can manipulate the pressure of a gas system, the temperature, the volume, and the moles or the amount of gas. And what we have seen using both Boyle's and Charles's law is that there's a predictable way in which these things will change when they interact with each other. So example, when you change pressure, how does the volume of the gas change when the other two things are held constant? So that's what we're going to be looking at on these slides. So let's go ahead and talk about our first gas law, which is Boyle's law. It is named after the scientist who actually first discovered this relationship. And it is a relationship between the volume and the pressure of a sample of gas. It is important to remember that when we are manipulating those two variables, that what we are keeping constant and is not changing is the moles and the temperature. So we need to make sure that nothing else is changing when we are applying Boyle's law, only our volume and pressure. We could say that the volume and pressure are inversely proportional, and that's a really important word, inversely proportional, when the amount of gas and the temperature is held constant. So what inversely proportional means is that when volume increases, pressure decreases, and vice versa. If volume decreases, pressure increases. So we have this relationship when one goes up, the other goes down. If we were to graph this relationship, it would look something like this. So this should be what your graph looked like. By having this relationship, we actually come up with an equation called P1V1 equals P2V2. And what this means is that if we have a gas sample and we know the initial conditions and we change, say, maybe the volume of the container, we could then predict the pressure that it would be in. Or we could predict the volume if we change the pressure and things like that. So we come up with this equation. 1 and 2, those subscripts just mean that we have this before and after scenario that we're looking at. So let's go ahead and look at an example problem where we are looking at how this law might actually present itself. So here's our example. A sample of gas has an initial volume of 3.95 liters at a pressure of 705 millimeters of mercury. If the volume of the gas is increased to 5.38 liters, what is the pressure? So let's go ahead and solve this problem using our Boyle's law. So let's identify some of our variables. So when you're coming across these types of problems, I like to think of what is my initial scenario and what is my final, or what is my before and what is my after. And by thinking about that, we can identify our 1 and our 2. So if we look at this, we have an initial, that is a hint that this is 1, volume. So this right here is going to become V1. And then we have a pressure of 705. So this must be P1. If the volume of the gas is increased, okay, so now we have a change in volume. So this must be P2. We want to know what is the pressure. Oops, excuse me, I said P2. This is V2. We want to know what the pressure is. So our unknown is P2. So I quickly labeled those so that I don't mix them up because it's really important that you keep them straight when you're putting them into the equation. So let's go ahead and do that. Let's plug these into the equation. So our equation is P1 V1 equals P2 V2. Now I want to get P2 by itself, so I'm going to divide both sides by V2 so that I have P2 all by itself on one side of the equation. Now I'm going to start plugging in my variables. So P1 is 705 millimeters of mercury. V1 is 3.95 liters. V2 is 5.38 liters. Notice that my liters cancel out And I'm left with units of pressure, and so those are going to be the units that I actually end up getting my pressure in. So we're going to go ahead and multiply 705 times 3.95, and then we're going to divide it by 5.38, and I get 518 millimeters of mercury, so 518 millimeters of mercury. And I went ahead, because all my original numbers had three significant numbers, or three significant figures, I expressed my answer with three significant figures as well. Now, before we move on, let's go ahead and think about, does our answer make sense, okay? So we know that if volume increases, our pressure should decrease. So if we look at our before and after, so we went from 3.95 liters to 5.38 liters. So our volume increased, which means what we should have seen is our pressure decrease. So my pressure went from 705 millimeters of mercury to 518. So that actually makes sense. That is a good way to check to make sure that you set up your problem right and plug things in correctly. All right, so let's go ahead and move on. Oh, let me clear that. Hold on one second. Clear. There you go. All right, so Charles's law. Charles's law is a relationship between volume and temperature. And what we are holding constant is pressure and moles. So the pressure of the gas system and the moles is being held constant. Volume is directly proportional to the temperature when pressure and the amount of gas is held constant. This direct proportionality is the exact opposite of inversely proportional, which means here that if volume increases, temperature is also increasing, and vice versa. If our temperature decreases, then our volume is decreasing, again, to make sure that because our pressure is staying the same. If we were to graph this relationship, which you actually did, you will see this linear line correlation showing that when volume increases, our temperature increases as well. With this relationship, we end up getting this equation. So notice that now we have volume over temperature instead of, in the last one, it was pressure times volume. So now we're dividing. Here before we were multiplying, here we're dividing. So we have V1 over T1 equals V2 over T2. Again, think of 1 and 2 as kind of like your before and after, or one scenario 2, so you have a change. One important thing to recognize is that when we are using this equation, and when you're using temperature just in general with these gas laws, is that you must express your temperature in kelvins. And that's really important, because if you don't, what you can actually get is you can get some negative volumes or negative pressure depending on the equation that you're using. And those two things are not possible in the real world. So we use kelvins to make sure that we are getting our correct units. So you want to always make sure that your temperature is expressed in kelvins. So let's go ahead and use this equation in an example. So a balloon with an initial volume of 3.2 liters at a volume temperature, that should just be at a temperature of 45 degrees Celsius, is warmed to 87 degrees Celsius. What is the new volume of the gas? All right, so I'm going to go ahead and let's get rid of that. I don't know why. That was a misprint. Okay, so let's go ahead and identify what variables we have. So we have an initial volume. This is V1. And we have a temperature. So this is going to be T1. And it's warmed to 87 degrees. So this means that this is T2. So what we're trying to find is V2. This is our unknown. I like to put a little question mark to say that's what I'm trying to find. Now notice that my temperatures here are in kelvins. So we need to make sure that we convert those into degrees, into kelvins. So I'm going to take my 45. I'll just label this as T1 to make sure I don't forget, is 45 degrees Celsius, and I'm going to add 273.15, and that's going to be able to convert me into kelvins. So 273.15 plus 45, we end up getting 318.15, and now we have kelvins. Notice that there's no degree signs when we talk about kelvins. T2 is 87 degrees Celsius plus 273.15. So we have 87 plus 273.15, and I get 360.15 kelvins. Okay, so now that I have my temperature within the correct units, I can go ahead and set up my problem. So again, it's V1 over T1 equals V2 over T2. Now I want to find V2, so I'm going to multiply both sides by T2 so that I can cancel out T2 on that side. And so I get this equation right here where I get T2 times V1 divided by T1 equals V2. You want to make sure that you are putting your subscripts and you label your problem correctly to make sure that when you plug things in, you don't actually mix up your temperatures. It's a really easy mistake. So let's go ahead and plug this in. So we have 360.15 kelvins times my initial volume, which was 3.2 liters. And we're going to divide that all by my initial temperature, which was 318.15 kelvins. And then that'll get us V2. So 360.15 times 3.2 divided by 318.15, and I get 3.6 liters. Notice that my kelvins cancel out, and so my units are liters. Now let's go ahead and make sure that this answer again makes sense. So we know that when volume increases, our let's go about this the other way, because what we see is a temperature. So when our temperature increases, which is what happens when it went 45 degrees Celsius to 87 degrees Celsius, our volume should also increase. And we went from 3.2 to 3.6 liters. So again, a good check to make sure that everything is right. So let's go ahead and look at our last equation. So we have this idea called the combined gas law, and it gets its name because it is really a combination of the Boyle's and Charles's law. It combines these two. And so what we have is now we can have a scenario where pressure, volume, and temperature are changing. So we can now change all three properties. The only thing that's being held constant when we look at the combined gas law is the amount of gas in the system. So the amount of moles. And when we get that, we get this equation right here. P1 times V1 divided by T1 equals P2 times V2 divided by T2. So if we look at this, notice what we have in this equation. This right here in blue, this should look familiar. This is Boyle's law. And if we do the same thing, notice what we have here. Volume over temperature. There we have Charles's law. So notice that we have these laws now built into this equation. So we combine these two laws and we get what's called our combined gas law, hence where it got its name. So let's go ahead and use and do an example to look at this problem or this equation. All right, there's definitely a lot more to keep track of when we're doing this problem. Whoops, let's go ahead and go back. And so when we look at this problem, a lot of stuff is changing. So what is the volume of a gas at 2 atmospheres and 200 kelvins if its original volume was 300 liters at 550 millimeters of mercury and 400 kelvins? Whew, there's a lot of numbers here. So let's go ahead and organize our work and start to try to kind of piece it apart to make sure. Now what I'm going to do for this problem, instead of labeling my work directly on that problem, I'm going to go ahead and write my known. So I'm going to write what is known in this problem up top. So we're going to label this knowns. Okay, so what is the volume of a gas at 2 atmospheres and 200 kelvins if its original volume? So that tells us, so if its original volume was 300 liters, blah, 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 blah. That tells us right there that that is your, we'll say P1, V1, T1 scenario. So I'm actually going to label the second part of the equation first. So we have V1 is 300 liters. We have P1 equals 550 millimeters of mercury. And we have T1, which equals 400 kelvins. All right. Now let's go ahead and look at our other part of the equation. So we are told a new pressure. So we have P2 equals 2 atmospheres. There's something going on here. Notice that my pressures are in different units. I will need to make sure that before I plug these numbers into my equation, that I either change them both to millimeters of mercury or both to atmospheres. It does not make a difference which one you convert them to, but they must be in the same units. And we are also told that T2 equals 200 Kelvin. So our unknown is V2. All right. So before we get started, let's go ahead and convert our units. I'm going to just choose atmospheres and convert this into millimeters of mercury. So 2 atmospheres. I know that 1 atmosphere equals 760 millimeters. Whoops, I ran out of room of mercury. So I'm going to take that, and that is going to be 14, 15, 20 millimeters of mercury. Let's make sure. 760 times 2. I hate doing math in my head because it's so easy to make mistakes. 15 and 20. Okay. So now that I have them all in the same units, you always want to make sure. And notice that my temperature is in kelvins, so we're good there. So let's go ahead and plug it into our equation. Okay, so we have P1 V1 over T1 equals P2 V2 over T2. All right. And our unknown is V2. So I'm going to isolate that. So I'm going to go ahead and multiply both sides by T2. If I do that, T2 cancels out. And then I could divide both sides by P2. So I'm going to go ahead and then put P2. So divide both sides by P2. And now I have V2 by itself. Pay attention to your subscripts, the 2's and the 1's, to make sure that you put things in the correct location. So notice that the first one is T2, and T2 is 200 Kelvin, times P1, which is 550 millimeters of mercury. And V2 is, V1 is 300 liters. Now I'm going to go ahead and divide that by P2, which is 1520 millimeters of mercury, and T1, which is 400 kelvins. Notice that my millimeters of mercury cancel out, my kelvins cancel out, and I'm left with units of liters. So I'm going to take 200, multiply it by 550, then multiply it by 300, and then I'm going to divide it by 1,520, and then divide it by 400. And I get my new volume to be 54.3 liters. Now, because there is so much changing, because we are changing more than just 2 things, we cannot really double check our answer. We can kind of look at a couple different things. We could say, okay, when we think about volume, pressure, let's see, from P1 to V1, we see that pressure is increasing, so we would expect volume to be decreasing. Okay. We see temperature is decreasing, and we would expect volume to decrease. So notice that they both are saying that volume should decrease, and it definitely did decrease. So in this case, we can kind of double check our answers. But sometimes what you'll have is one says that volume should be increasing and one says that volume should be decreasing. So it might not be so easy to check your answers. In this one, it was pretty easy since both of our situations tell us that volume should be decreasing, and it does. So what you have now is you have now some practice problems that you're going to be working on.